Okay, we're gonna do 519 and 520 in your book if you have your book. We're gonna do another. These are conservation of momentum problems, but they're a little more challenging because now we're gonna actually think of them as real vectors with at different angles and stuff. So we have to do some vector problems. So we're gonna work on this problem here. 519. We got a 2 kilogram ball rolling east at 10 meters per second. It's going to collide with a stationary 4 kilogram ball. So that's what we can draw for before the collision. So we'll go ahead and maybe just draw that in real quick. We have a 2 kilogram ball moving along at 10 meters per second, and it's going to hit a 4 kilogram ball. And that's before the collision. So we can figure out all momentum stuff, vectors before the collision. After the collision, it says the 2 kilogram ball is then going to leave the crash scene at 7 meters per second at 20 degrees north of east. So I'm going to draw a grid here. And this 2 kilogram ball is going to be going like this at 7, and this is 20 degrees. That's the 2 kilogram ball. And then, so what is the velocity of the 4 kilogram ball? Well, if the 2 kilogram ball comes in here and glances off and goes up like this, then the 4 kilogram ball is clearly going to have to, do something like this. If you've played pool, then you would know this. So I want to figure out what's the velocity of this, 4 kilogram ball coming down like this. These are all vectors, so it could be kind of challenging. So what we want to do first. We want to figure out the velocity, not actually just the momentum. We want to figure out what's the velocity of this ball down here. Okay, so conservation of momentum. So momentum before the collision is equal to momentum after the collision. So before the collision, what do we have? We have a 2 kilogram ball moving at 10 meters per second, 2 times 10, plus the 4 kilogram ball not moving at all, so that'd be 0. So before the collision, we have a 20 kgms, 20 kgm per s. Sorry, okay, and that's the momentum before the collision, and it's going in this. Remember, momentum is vector, so we have to draw that. So it's 20 kgm per s going this way. So we're going to write this into I hat j hat form. So before. We'll call it vector before, okay, is going to be equal to 20 I hat plus 0 j hat. It's all going to the right and no going down or up. Okay, that's the momentum before. All right, so afterwards, what do we have for momentum vectors? Well, we have the ball 2, the 2 kilogram ball. How do I want to write this? After, and we'll call it the 2 kilogram ball. The vector for that would be the total momentum for that is 7 times 2, right? It's 14. So it's 14 kgm per s. But I need to get the components of this. So this vector here is going over and up. And you might be tempted to figure out these components with the velocity, the speed. We don't want to do that. We want to actually do it with the momentum vector. So I take the 7 times 2, and I get the momentum, but the momentum vector is 14 kgm per s at 20 degrees north of east. I want to resolve this momentum into its 2 components. So this one over here, this I hat here, is the opposite side. So this would be 14 sine of 20. And this one in here would be the 14 cosine of 20. This is my I hat. This here is my j hat. I might have just misspoke. This is my j hat. And right here, this one here is my j hat. This one down here is my I hat. So my I hat is 14 cosine of 20. So remember, when we did vectors, we kind of memorized a thing that if we did all the angles from north, that I hat would always be sine. But if we don't do that, we didn't do from north here. We just did this angle in here. This is the opposite side, and this is going up and down. So this is j hat, and my adjacent side here is I hat. So my j hat here is 14 sine of 20. My I hat is 14 cosine of 20. I hope that makes sense. Okay, so So if I do that out, my I hat is 14 cosine of 20. And if I put that in the calculator, I get 6.84 for my I hat, which makes sense. It's going to the right. It should be a positive. And then I did that wrong. I'm sorry. That's something that's coming up later. My I hat, I think, is 13.16 I hat. Still makes sense. It's positive. And the J hat is, if you put in 14 sine of 20, you would get a 4.79. Okay, so how do I find, that's J hat. How do I find the vector component of the momentum of the 4 kilogram ball after the collision? So after the collision, what's the components of the 4 kilogram ball? Well, we know before the collision, the total momentum is 20 I hat plus 0 J hat, right? We figured that out from down here. That's before the collision. We know that the momentums after the collision need to equal that. So what we can do is we can take this before the collision and subtract this momentum right here. Take the momentum before the collision, subtract the momentum vector after the collision of this one, and that should give us then this momentum collision here. So I'm simply going to subtract 20 minus 13.16 is a 6.84 I hat. And 0 minus 4.7 is a minus 4.79 J hat. This is the component then of the 4 kilogram ball. So it looks like this. It looks like a momentum of 6.84 over, and a 4.79 down, and then here is your resulting momentum. So I can figure out this angle. I can figure out the angle by doing tangent of that angle is 4.79 over 6.84. Remember, these are still momentum vectors, so that's important. But I can still find the angle that I need for my end of the problem by doing this. And if you figure that out, that angle was around 35 degrees. 35 degrees. Be right in there. Okay. And if I want to find the total momentum vector, I use Pythagorean's theorem. And if I do that, I think I got 8.35 as the momentum. Okay. So the momentum vector would be 8.35 kgm per s at 35 degrees south of east. But what I actually want is the velocity vector. So that's easy to do. All I do is take 8.35, because momentum, remember, momentum is mass times velocity. So you find the velocity, you take the momentum divided by the mass. So I'm going to take this 8.35 and I'm going to divide by the mass. And if I do that, I get a 2.1 meters per second. And the angle is still the same. The momentum angle and this angle here, this 35 degrees, is the angle for the momentum vector, but it's also the angle for the velocity vector. So I can say 2.1 meters per second at 35 degrees south of east, or I could say at 125 degrees. If you just want to go from north, all the way from north, you just put the 90 and then the 35 degrees. Okay, so that is how to figure out the velocity vector of one of the balls. So you have the momentum before the collision in vector format right here, and you get the momentum after the collision of at least one of the components, and you could subtract those and get the momentum components of the other ball. And then you simply divide that momentum by the mass, and you'll have the velocity vector of that. Okay, hope that made sense. You can pause it and go back and forth and look at it some more. There's a follow-up question to this. The follow-up question is, what was the percent kinetic energy loss in the above problem? This is actually pretty easy because kinetic energy is not vectors, so we don't have to do anything with the vectors. So we can just say, what was the kinetic energy, total kinetic energy before? And we can figure out what was the total kinetic energy after. And then we can just see how much, what percent we lost. So before, you remember we had one half mv squared is kinetic energy, right? So before we had 1/2 the 2 kilogram ball was moving at 10 meters per second, so this would be 10 squared, and the 2's would cancel out, and 10 squared is 100. We had 100 joules of energy before. Remember, the 4 kilogram ball wasn't moving, so it had no energy. So before the collision, we had 100 joules of energy. That'll be easy to do a percentage since it's 100. After the collision, we had 1/2 times the 2 kilogram ball, and it was moving at 7 squared, so that's its energy. And the other one, see, we can just add their energy. We don't have to worry about the vectors. There are no vectors with kinetic energy. The other one was 1/2. It was a 4 kilogram ball, and it was moving at what our final answer was at 2.1 meters per second, and I'd square that also. Okay, so if you do that, for this you get 49 joules, and for this one I think you get like 8.82 joules, for a total afterwards of 57.82 joules. So before the collision, this is how much energy we had. After the collision, this is how much energy we had. So it's asking for what's the percent kinetic energy loss. So I'm going to do 100 minus the 57.82 to figure out how many joules I lost, right? And I'm going to divide that by the amount of energy I started with, which is 100, okay? So if you do that, that will end up being like a 42.2%. 42.2% energy loss is the final answer for 520. Okay, so this was an inelastic collision, which is why kinetic energy was lost. Kinetic energy is not vector problems, so you can just, totally subtract it. Find out the energy before, find out the energy after, and just subtract them. Momentum are vector problems, though, so they're not as easy as just adding and subtracting, unless they're like the last video where they were going just left and right, and yeah, you are then just adding or subtracting. But if they're going at angles, you actually have to find the components of those momentums and add or subtract those components and work it around that way. So I know this is kind of probably very challenging learning this online, but keep on trying and ask questions in the on the text channels, and we'll get all your ELAB problems done, and so you'll be able to ready to take this test on Friday.